So let's go over the rest problems together. The first problem is first order linear ordinary differential equation. So we convert it into standard format by getting rid of the extra coefficient in front of my derivative term. Keep in mind that you want your expression to look like something times y, so it means you also need to absorb the negative sign with it. So the rest part is quite straightforward. Don't forget your formulation is supposed to be integrating factor is integration e to the power of pt dt, and therefore all I did is set my integrating factor, and then I use substitution method to carry out my integration. So once I found out what exactly is supposed to be my integrating factor, which is essentially this one here, right? So sorry, I skipped some steps. So my integrating factor is technically t plus 1 to the power of negative 0.8. So what I end up with is my integrating times factor times y taking derivative is supposed to be equivalent to the right side of my expression. I updated 16 over 10 to 8 over 5. So my right side of the expression times my integrating factor. So the derivative of something equals a t-dependent expression. So all I need to do is integrate both sides. So if I were to carry out my antiderivative calculation, you will be able to get my final answer, which looks like that. So you can fill it in. My u of t is supposed to be t plus 1 to the power of negative 0.8. And my final answer is, I typed it out down here. Well, this is how my y should look like, but don't forget you have an initial condition, so I substitute 16 for y. I substitute 0 in for my t, so it's 8 over 5, this is gone, times that term plus c times 0 plus 1 to the power, so c times 1. So I have my expression here where c can be easily solved. Therefore, I end up with my final answer, which is 8 over 5 times 5t plus 6.525, add to 6 times t plus 1 to the power of 0.8. So that's supposed to be my final answer for this problem. Bottom line, it's integrating factor method. So keep going. Well, the next problem is again first order linear ordinary differential equation. So we use integrating factor method. I rephrase my expression to look like the standard form. I find my integrating factor to be e to the power of antiderivative of this term. So whatever my integrating factor is, multiplied by my left side expression y takes the derivative equals my right side times our integrating factor. So if I were to take antiderivative of this, the left side is simplified. The right hand side, I'm going to use integration by part method, where v is my x, The other piece, the w, is 1 over 4e to the negative 4. Hence, dw is exactly what's left, negative e to the negative 4x dx. So what I end up with is my v times dw, which is equivalent to vw minus antiderivative w dv. So I can carry out the rest part of the calculation, and there's no initial condition given to me, so whatever I found, all I need to do is to get rid of this extra term on both sides, so I end up with y equals this whole thing divided by e to the negative 4x. Hence, I have x over 4, the e to the negative 4x canceled out. 1 over 16, again, e to the negative 4x canceled out. And then c divided by e to the negative 4x, which is c times e to the positive 4x. So I have my final answer here. It's e to the power of negative 4x. And this one is supposed to be x over 4 plus 1 over 16 plus c times e to the power of 4x, where the c is not really given to us. Initial condition is not given to us, so we can't really identify the c. The next problem here, again, first, it is an initial value problem. It's first order linear ordinary differential equation. So once you have, well, it's already of the standard form. So you can find your integrating factor by using e to the power of antiderivative of the coefficient of y. Once you find your integrating factor, the derivative of integrating factor times the answer you're looking for equals the right-hand side multiplied by your integrating factor. So all you need to do is to integrate both sides. The left side is as simple as throwing away the derivative. The right side, taking the antiderivative, and make my life easier by putting out the 8. The rest part, technically I want to do integration, but it's best idea is to integration by substitution method, where I claim e to the sine x is u. So e to the sine x times derivative of sine x, which is cosine x times dx, is the same as du. So everything underneath it is equivalent to du. So I actually have 8 times antiderivative du. I can easily get to the final answer and write it back into the x format. So what I found is y times e to the sine x is 8 times sine x plus c. All I need to do is get rid of e to the sine x. So I end up with y equals 8 plus c e to the negative sine x, because I'm dividing by it. There's an initial condition given to me, so I'm plugging in and plugging 10 for here. And it's 8 plus c times e to the power of negative sine 0, hence e to the 0. So it's 10 equals 8 plus c. In other words, c is 2, so I can find my final answer relatively easily with the c substituted in. So problem number 14, what you are going to do is it's an initial value problem again. Since we are not super familiar with the structure, I rewrite it as y prime plus negative 1y equals at, where y2 equals negative 7. So once we convert it into the structure you like, you are going to be able to find the integrating factor, which is e to the antiderivative of negative 1 dt. And then what you end up with is to the integrating factor times y takes derivative equals the right side of expression times times integrating factor. All you need to do is integrate both sides. The left side simply throw in with the derivative. The right side needs you to calculate the antiderivative. The antiderivative calculation is not too bad. You are going to be, again, using the integration by parts method. So I directly jump to the calculation, final answer with some kind of help of online calculator. So once I did this, I end up with e to the negative t equals y times y equals this whole thing. So all I need to do is to multiply this e to the t, or divide it by e to the negative t, to both sides of my expression. So this is gone. I have y left. This term, if I divide it by e to the negative t, I have negative 8t left. So negative 8t left. This term, if I divide it by e to the negative t, it is 1 left, so that's why I have 1. Again, this term divided by e to the negative t is c2 times e to the positive t, so this is what I end up with as my final answer. And don't forget, plug your initial condition, so negative 7 equals 8 times negative 2 minus 1, hence negative 3, plus c times e to the 2, so plus c times e squared. Therefore, you end up with negative 7 is negative 24, move to the other side, negative 7 plus 24, which is 17. So you end up with 17 being c times e squared, hence c is 17 divided by e squared. You plug it back into your final answer. So your final answer is negative 8t minus 8 plus 17 over e squared times e to the power of t. The last problem, I write down the conceptual process to solve it, but because the final answer in the system is wrong, so I simply delete this problem. It was not easy to fix the solution, so I delete it. I hope you actually look through the process, you understand how to conceptually solve it. It's essentially still first order linear ordinary differential equation. We're going to solve it with integrating factor method.